is Sarah Tepfer, and I'm a graduate student at Harvard University. Today I'll be talking about future mold problems, hygrothermal issues in U.S. single-family residences. This study is based on two observations. First, building envelope design is climate-specific, and second, climates are changing. This diagram addresses the first observation about vapor barrier placement, which is climate-specific. In a heating-dominated climate, we typically place the vapor barrier on the inside of the building envelope, as shown in these two diagrams. This is optimal in the winter months when you have warm, moist air on the inside of the envelope, which the vapor barrier prevents from migrating towards the cool air. Such migration could lead to moisture problems in the envelope. This condition, however, becomes suboptimal in the summer months when you have warm, moist air on the outside of the envelope, which is allowed to progress through the insulation layer towards the cold air. This leads to the potential for moisture problems within the envelope. The second observation is based on climate change. These graphs were produced using data from WeatherShift, which show the present day average monthly temperature in the gray and the subsequent warmer temperatures for 3 time horizons across 3 different warming percentiles, with 95th percentile representing the most warming. We can see from these graphs that we do project climate change, especially warming. So that leads to the question of what happens when you have a New England style wall, which you see here, with a climate that is becoming increasingly like the southern United States. This leads to the following hypothesis. Wall conditions that perform well hygrothermally under historic conditions will show mold growth under future conditions. This presents a health issue. As this diagram shows, there are several pathways linking sources of dampness and mold with health. Some of these sources may be from surfaces in roofs, floors, or walls, or structures, as shown in this diagram. Other problems related to moisture and mold in structures and surfaces are building degradation issues, as well as energy performance changes. This study basically leads to a key question. What will the hygrothermal performance of newly built code-compliant residential building envelopes look like under future climate conditions across the US? The scope of the study is climate zones 4, 5, and 6A, which are mixed humid climate zones under the ASHRAE climate zone model. And we are also looking at new single-family residential construction. Our methodology was to morph existing weather files in WeatherShift to create future climate data. We then ran code-compliant wall assembly through a hygrothermal model in WFI Pro using the future climate data. We then used outputs from the hygrothermal model to determine mold growth risk according to the VTT model. This table shows the most populous cities in climate zones 4A and 5A and 6A, whose codes require vapor barriers. As highlighted in yellow, each of these cities' codes does require a vapor retarder on the interior side of the building envelope. Our code-compliant wall construction then became a vinyl-clad wall, which we found to be the most typical cladding system for these cities. An air gap, an air barrier, oriented strand board, fiberglass bat, a vapor retarder, and gypsum wallboard. While we looked at conditions across the building envelope at various locations, as shown by the circles, we focused on the conditions at the intersection of the fiberglass bat and the vapor retarder on the warm side. This led to the following results. Each of these graphs represents the mold index for a different city. Mold index is a metric used by the VTT model, which ranges from 0 to 6, and a mold index above 3 represents a very problematic condition. The green lines show the mold index for the present day. As we would expect, there is no issue across these cities. This suggests that the walls are working well, which is what we predict. However, when we look at the 50th and 95th percentile warming scenarios for 2080, we see a different story. For several of these cities, for even the 50th percentile warming scenario, we do see mold index rise above 3. We can look more closely at several cities like Raleigh, Omaha, and Milwaukee, where the 50th percentile warming scenario does show a mold index above 3 for 2080. These graphs show the equilibrium mold index, or the mold index at the end of the 10-year observation period. As you can see from these graphs, which show the TMY, or present day, the 2026 to 2045, the 2056 to 2075, and 2080 to 2099 equilibrium mold indices. For climate zones 4A and 5A, we don't expect much of an issue until mid-century. For Milwaukee and climate zone 6A, it's hard to say whether a problem will occur. It seems that by the end of the century, the mold index is hovering close to 3, but couldn't potentially be rising above it. This leads to the following conclusions. Lightweight timber building envelopes constructed to today's code requirements are not well adapted for future conditions across several climate zones in the US. This finding implicates a large number of single-family residential dwellings in the US and suggests the need for the consideration of climate adaptation and resilience in the development of building codes. Thank you.